And let me stop my video. All right, so the ene is telling me that's an alkene present. And then on that chain, I have a group I have a substituent at 2. And I got another substituent here. All right, so that group at 4, that's a methyl group. That's a CH3. Remember, at the end of every line is a CH3. So that's a methyl. And then this group right here is what we call an isopropyl group. Right? Notice it's 3 carbons. 1, 2, 3. Right? So the propyl part is because it's 3 carbons. The iso prefix is because of where the chain is attached, right? It's attached at that middle carbon right here. So that's why we call it an isopropyl. So those are your 2 substituents. All right, and then so it's going to be 2 isopropyl, 4 methyl, 1 pentene. Right. So when you're looking at an example like that, that kind of has like the alkene kind of it's kind of external to the chain. You still have to count from that end where the alkene is, especially since it's terminal. Does that make sense?
Can you repeat that one more time?
Did we name the other one already? I think we did, yeah. All right. Any other questions? Any questions about that example?
Can you repeat that one more time, Dr. Russell?
Say that one more time. Your audio is kind of low.
Can you repeat that one more time?
About which part?
The I guess the alkene part.
Yeah, so it's kind of external, right? It's not like what we normally used to seeing where the alkene is somewhere in the chain, even though this alkene is terminal. So it's at the end and then it's got a bunch of stuff connected to it like that. If it's terminal like that, you always want to start counting at the alkene.
What if it's not terminal? Then what do you say?
Then you count from the end that is closest to, like we did up here, right? Because that's not a terminal alkene, but we started counting right here. And now down here. Right? If it's not terminal, then you find the end that is closest to, and you start counting from there. All right. So we looked at the nomenclature for those 2. Let's go down here and let me move this up because I need this space. All right, let's see if we can figure these out. So it's this number 3 says give the structure corresponding to each name. And it says 3,3 dimethyl cyclopentene. So let's start with the parent. The parent is cyclopentene. All right. So what does the cyclo mean? Anybody remember that? We kind of talked about it. We haven't talked a lot about it, but we did talk about it earlier, like in the first few weeks of class. So when you see that prefix cyclo, that means that it's a ring. Right, so that this is telling me that this is a ring. Let me pick a different color. That sucks. That's a ring. The pent means the ring has 5 carbons. And the ene means that there's an alkene in the ring, a double bond in the ring. All right, so this is a 5 carbon ring. That looks like that. All right. And then because it's a ring, we're going to start counting here. So that's 1 and that's 2. Either way you count, you can count from the other side too, it doesn't matter. But the double bond in a ring, we call this a cycloalkene. Again, ene is telling me that there's a double bond present. The double bond is always 1 and 2. All right. And then it says 3,3 dimethyl cyclopentene. So that means on carbon 3, there's 2 methyl groups. Right, that's carbon 3. Are y'all following?
Could you put that, since it's a ring, could you put that double bond anywhere in there?
Yes.
Just,
Yes.
You just have to start from there when you start counting.
Yes, it can be anywhere in that ring, but when you start counting, the double bond is going to be 1 and 2 automatically.
Okay.
Now, here's another piece to that. If you already had the structure, right? What you want to do when you're numbering, you're not going to do this 1, 2, 3, 4, 5. That would be wrong. And the reason is because you want your substituent or substituents to have the lowest possible number. So in this case, you're going to start numbering to give that the dimethyl the lowest number possible. So that's 1, 2, 3. Right? If you had the structure without the name, right? You would always number. You're always going to number so that your substituents have the lowest number possible.
But the double bond will still start at 1 and 2.
Yeah, yeah. But what I'm saying is that you wouldn't label this one 1 and that one 2 and then go around the ring the other way. You follow what I'm saying? Because then that's going to make your dimethyl substituent 5, when if you number like we have in black, it's going to give it a number. It's going to make it 3. Does that make sense?
Yes.
All right. All right. So let's do the other one. Let's do the next one. It says trans 2-heptene, trans 2-heptene. All right. What does that trans mean?
The substituents are on opposite sides.
Okay, good. How many carbons in that? What does the hep mean?
4.
7. 7 carbons. It's methyl or methane, ethane, propane, butane, pentane, hexane, heptane, octane, so on and so forth. All these Greek prefixes. So the hep is 7 carbons. And then it says the ene is telling me that it's an alkene. And then the 2 That's the location. Of the double bond. Sometimes you'll see it written as hep2-ene, where the parent is broken up with the location of the double bond. So you might see trans hep2-ene, but both conventions are okay. But the 2 is the location of my double bond. So I need a 7 carbon chain. I'm just going to draw one out. Right, and if you're doing a skeletal form for just a straight chain alkane, if it's 7 carbons, it's 6 strokes, 6 pencil strokes, or 6 pen strokes, right? And then I'm going to number this as, I'm just going to put the numbers in 1, 2, 3, 4, 5, 6, 7. All right, where am I going to put my double bond?
Would it be between 2 and 3?
Between 2 and 3. Because this is 2 heptene. So remember, the location of my double bond is going to have the lowest number, but it's going to be between 2 carbons, right? So if it's between carbon 2 and 3, is going to have the number preceding the parent to tell me the location is going to be the lower number. So it's 2 heptene. All right, and then is that trans? Does that satisfy the trans part also?
Yes.
So I got carbon 1 over here and then carbon 4 on the opposite side. So that's trans 2 heptene. All right, let's do the last one. And then we're going to do some of these degrees of unsaturation problems. And then we're going to move on to start some of these reactions. All right. So here, cis 4 octene. What's the parent? Octene. Right. What is oct?
8.
8 carbons. Right. You know, you got an alkene present because of the suffix ene. Right. You know that your double bond is going to be located between carbon 4 and 5. And it's going to be a cis double bond. All right. Because of the stereochemistry indicated right here. So let's draw the double bond in first. So I'm going to do that like that. So this is 4 and this is 5. Right. We know that because it's 4 octene. So the double bond is going to be between carbon 4 and carbon 5. So, but the fact that it's cis, I need to make sure I indicate that. So this will be 6, 7, 8. Is that right? This is carbon 6, carbon 7, carbon 8. And then at carbon 4, since it's cis, this has to be 3, 2, and 1. Like that. So the double bond is cis. You can see that right here, where both groups that are not hydrogen are on the same side. And we got 8 carbons total. All right, so that's 1, 2, 3, 4, 5, 6, 7, 8 carbons total.
Are you saying carbon 3 and carbon 6 are on the same side?
Mm-hmm.
Versus?
Yes.
If it's this, should we draw the double bond first, like you did?
That's a strategy. That's a good strategy. Put the double bond in and then make sure it's cis, and then you can attach whatever else you need to attach. All right, any questions about those? All right, let's go up here. I'm gonna just take this. I want to talk about the degrees of unsaturation right quick, and then we're gonna come back and start working through We put a date here. What's the date? The 20th. We'll come back and start working through some of these other problems. All right, so with when we talk about degrees of unsaturation, you also hear this referred to as the index of hydrogen deficiency. Right, IHD index, I'll write that out, of hydrogen deficiency. Right, so when you talk about something being unsaturated, then try to do that. Right, when we talk about unsaturation, what you're talking about is the presence of pi bonds, right? Double bonds, triple bonds. But it also, what this number would tell us is the number of rings, because anytime, and I'll show you, so this is going to indicate the presence of pi bonds or rings. And I'll show you why I'm saying that. So if I have a 6-carbon chain, right? That carbon chain, if there's 6 carbons, let me show you. Then the formula for that alkane is going to be CnH2n plus 2. Right? So if I put in 6 for N, right? Then H is going to be 2 times 6 plus 2, which is 14. So C6H14. This is the way I calculate, or the way I determine the molecular formula for an alkane, CnH2n plus 2. All right. So on the end of each one of these carbons right here, this is a CH3. Right, and that's just a regular alkyl chain. What will happen if I wanted to combine or close this chain up and make it into a ring? So I want to take this carbon right here, I want to make it into a 6-member ring. So let's take this carbon, put them together. What would I have to do to each one of those carbons?
Move, is it a proton or a hydrogen?
Say that one more time. I think I heard you, but it was kind of muffled, and I think you're right.
I said remove a proton or I think the hydrogen.
Yeah, you're gonna have to take a hydrogen off, right? Because right now, if you look at this ring, every space is occupied by hydrogen. Is that right? So this ring is what we call saturated. Right? So all the spaces on carbon are occupied by hydrogens. So it's saturated. But if I wanted to close that up into a ring and make it a 6-membered ring, by attaching the 2 end carbons, I'm gonna have to remove 2 hydrogens. Right, so if I wanted to close this up and take this carbon and attach it to that carbon, 2 of my hydrogens have to go. So in order to cyclize it, we have to remove 2 H's. Right, so that's, and I'm gonna put, I'm gonna make these pink. Right, and up here, I'll make these pink. Right, so if I want to cyclize it, I need to take off a hydrogen on each one of those carbons. Right, so that's why when we talk about unsaturation, we're talking about the presence of a ring, because in a ring, at least 2 of the carbons in that ring, if I were to cyclize it from a chain, had to lose a hydrogen, right? So every space is not necessarily occupied by a hydrogen, because you got at least 1 carbon-carbon bond. That's the result of taking away 2 hydrogens. And it's the same way if I took that same compound, right? And I'm gonna put, again, these are my CH3s. If I want to add a pi bond, in this case, let's just say a double bond between these 2 carbons right here. What would I have to do?
You're gonna have to get rid of hydrogens.
Same thing, right? I can't have the same number of hydrogens on that carbon, on those 2 carbons. I need to lose 2 hydrogens. So we're gonna say we're gonna lose this one and this one. Right, so you got to lose two hydrogens. So this is also what we would call unsaturated. Right, because it's not, I got 2 spaces on that chain that are not methylene carbons or CH2s, right? So when we talk about degrees of unsaturation, we're looking at what it can tell us is the number of rings that are present, or the number of double bonds that are present, or pi bonds that are present. And that's important because if we have a molecular formula, let me just paste this down here somewhere. Like the first one, C2H2, let's see if we can figure out how many degrees of unsaturation are present there, right? So this C2H2, and we're going to compare that to CnH2n plus 2, right? So we're going to put the number in. So we got two carbons. So we're going to put that number in down here. C2H 2 times 2 plus 2. Is that right? So 2n, n is the number of carbons. So I'm going to stick that number in there. So it should be what? C2, H6. Is that right? That's what it should be, yes?
Yeah.
All right, so to calculate the degrees of unsaturation, we subtract out use a simple formula. Href is the reference compound. So this is my reference, CnH2n plus 2. We're going to call that the reference. This is what we call Href. All right. And then H molecule, I just abbreviated as H mol down here. That's going to be this number right here. Right. So if I take Href, which is 6, and I subtract out H molecule, right, which is what? 2,
Mm.
and divide that by 2, the degrees of unsaturation is 2. All right. So Href minus H molecule divided by 2. So H molecule is 2, Href is 6. I subtract them out, divide by 2. 6 minus 2 is 4, divided by 2 is going to be 2. All right. What that means is that for that molecule is either going to be 2 rings or 2 pi bonds. But with 2 carbons, you cannot make a ring with 2 carbons. You have to have a minimum of 3 carbons to make a ring. So that's not enough for to make 2 rings. Are y'all following that? So a potential structure that would match that would be something like this, right? Just a simple alkyne. All right. It's got 2 carbons, it's got 2 hydrogens, and it's got 2 pi bonds. All right, that's a pi bond. This is arbitrary, right? I could pick any 2 of those and call it a pi bond. And that's a pi bond. Right. And so the degrees of unsaturation tells me, again, the number of rings or the number of pi bonds. And so since we have only 2 carbons, we can't make a ring, period. So it's got to be, that compound has to just have 2 pi bonds in it. Are y'all following? Anybody got a question about that? We're going to do a couple of more of these too. So
So to make,
go ahead.
go ahead, yeah.
So you won't be able to necessarily make a ring and be tied depending on the degree of saturation.
Yeah, you can't make a ring unless you have at least 3 carbons. And this, the fact that you got 2 degrees of unsaturation, that will mean you need either 2 rings or 1 ring and 1 double bond, right? Or 2 double bonds. Or not double, let me not say double bond, 2 pi bonds. Right. So the only thing that'll match and allow us to stay with that molecular formula is the structure, the alkyne I have on the bottom. Right, because it can be any combination of rings and pi bonds. It can be, again, if the degrees of unsaturation is 2, then you can have 2 rings, you can have 1 ring and 1 pi bond, or 2 pi bonds. And the more degrees of unsaturation you have, the more combinations you can come up with. Let's do another one. Let's do C6H6. Got to put another page in. All right, let's do C6H6. So C6H6, and again, we're using this formula, HREF. Come on, Russell. Minus H molecule divided by 2. All right, and then we're gonna do 2 more of these. We're gonna do one with a halogen and one with group 5 because that's a special case. Though both of those are special cases. All right, so C6H6. What is how do we calculate HREF again?
She, and then
Is that right?
yes,
Right, so that's gonna be my reference compound. So it's gonna be C6H2 times 6 plus 2. I think I sent this out too, like early, like when the first couple of weeks. I think it was in one of those videos that it dealt with degrees of unsaturation in there too. But it's okay. We're gonna roll with it. So C6H what? 14. Was that right?
Yeah.
So HREF is 14. Yeah. And then H molecule is 6. So 14 minus 6 over 2. That's 8 over 2. That's 4, right? So you got 4 degrees of unsaturation. And 6 carbons. 6 carbons is not going to be enough to make 2 rings. Or will it? Let's see. 1, 2, 3, 4, 5, 6, maybe. So the 2 rings will be 2. I guess you can do something like that. Right? That's 2 rings and then 2 pi bonds. So that will work. And you got 1, 2, 3, 4, 5, 6 carbons. Or you could do something like this, like benzene, where you have 1 ring and 3 pi bonds. Right? That satisfies 4 degrees of unsaturation. Go ahead, Tia.
Did you said 6? Oh, 6 carbon.
Yes.
Oh,
I'm following the molecular formula that was given to me.
oh,
C, which is C6H6. Right, and so that based on that molecular formula, there are 4 degrees of unsaturation. So that, that means I can have 2 rings, 2 pi bonds. I can have 3 pi bonds in 1 ring, any combination, right? I can have 3 rings and 1 pi bond, but I don't have enough carbons to make 3 rings. I could have 4 pi bonds, which if I had just a 6 carbon chain, we could show that too. 1, 2, 3. I don't think we can fit 4 in there. 1, 2, 3. No, that won't work. Right, because I'm only satisfying 3 of the 4 degrees of unsaturation, so that's not going to work. Right, but these 2 match. So C6H6, that will match, and they would satisfy the fact that we got 4 degrees of unsaturation.
I have a question.
Go ahead.
So, I remember you said earlier it won't be like enough to make a ring. How many carbons do you need to at least make a 1 ring?
3. You need a minimum of 3 carbons to make a ring, because you can make a cyclopropane ring. You can make a cyclopropene, right? So you need at least 3 carbons to make a ring for it to
Okay.
to be able to cyclize.
So on the top, I guess ring,
Mhm.
I guess I'm not seeing how you're able to add the double bonds.
Oh, yeah, so here, like, let me show you. So if I didn't have the double bonds, right? All of these carbons on the end, every vertex is a CH2. Right, we know that. Like so, right? And then there's a hydrogen. Fix that. Shucks. Right, there should be one hydrogen here and one here. Right, but if I put a double bond in here, I just need to remove one of the hydrogens. And the same thing on the other side. I can put a double bond in there and take off one of the hydrogens.
I have a question.
Go ahead.
I'm still not understanding how that ring is satisfying the 4 degrees of unsaturation.
There's two of them. You see how it's two four, it looks like two 4-member rings.
So it's 2 separate rings, is not one?
Two rings. This bond right here in the middle makes this bicyclic. Like, so you got two rings fused together.
Oh.
This is ring 1. And then this will be ring 2. So that's 2 rings and 2 double bonds.
Okay.
All right. Let's do another one. Let's do E and F. We're going to do those together because that gives us a chance to talk about some other rules about this. I'll just add another page. Didn't plan on doing this forever, but might as well do it now because when you see it again, it'll click. We'll do E and F on the same page. Get down here. So E and F are special cases, right? Because with E, you have a halogen present. Right, and with F, you have a group 5 atom. Right, so when you have a halogen present, if you have, and it doesn't matter if you have 1 halogen, 2 halogens, 5, you're going to subtract 1 from href for every halogen that's present. So halogen, anytime you have a halogen, that's a special case. So you'll subtract 1 from href. Sometimes in the book, you might see it the opposite. It might say add 1 to H molecule for a halogen present, but you want to subtract 1 from href. This is the way I teach it, but there's another way to do it too. You'll add 1 to H molecule, but for us, we're going to do it this way. All right. If there's a group 5 atom present, you're going to add 1 to href. For each group 5 atom. All right. So that's how we're going to approach that. So let's take E. E is C7, H11, Br. All right. So href is 16. 2 times 7 plus 2 is going to be 16. Is that right?
Where you get 7?
Huh?
Where you get 7 from?
2 times 7, 2 times 7 is 14, plus 2 is 16.
I thought we used the,
We're not doing anything with that yet. Did you add 1 already to it?
no, I thought we used the number of hydrogen.
No. It's 2N. And then for N is the number of carbons. So
Oh.
2N plus 2. That's what we getting for HREF. So it's 2 times 7 plus 2. So it's 16. And then H molecule is 11. You can see right away that this is going to give us an improper fraction, right? It's going to be 5/2. So we need to subtract 1 from HREF because of the halogen, right? We've got a bromine present. So we're going to take that 16 and subtract 1 from it because of that halogen. And if you have 2 halogens, you'll subtract 2. If you have 3, you'll subtract 3. However many halogens are present, you're going to subtract 1 from HREF for each one of them. Right, so that's going to be 15 minus 11 over 2, which is 4/2, which is 2. So that's 2 degrees of unsaturation. So that can be 1 ring, 1 double bond, 2 rings. It can be 2 double bonds, or not. I keep saying double bond. It'd be 2 pi bonds. So there's a couple of combinations we can look at when we're trying to propose a structure, right? And then for the other one, C5H9N, let's do that one. Right, HREF is going to be 12. Right, that's 2 times 5 plus 2 is 12, right? 2N plus 2. HREF is going to be 12. And then H molecule is 9. So you can see again, if we were to not do anything, we're going to come up with an improper fraction, right? It'll end up being 3/2. So what we want to do is, again, if it's group 5, so you got nitrogen that's group 5, you're going to add 1 to HREF. Right, so add 1 for N. So that now that'll give us a 4, right? So we got 4 degrees of unsaturation. So we can come up with a lot of different structures for that. Let me see if, can anybody, how much time we got? We got a minute left. Can somebody give me one structure you think will match that? Look at the molecular formula. You got C5H9N.
Wait, Dr. Russell.
Yes.
So like if you subtracting 13 minus 9 divided by 2, like so it wouldn't be 4 divided by 2.
My bad. You're right. It's 2, not 4. My bad. Thank you for catching that. So you got 2 degrees of unsaturation. So 2 rings, 2 pi bonds, 1 ring, 1 pi bond. Can anybody come up with a structure that might match that? We only got a minute left, so I'm gonna use it wisely. All right, what if I did this? So if I have a 5-member ring and I put a double bond in the ring. That's my 2 degrees of unsaturation. So how many hydrogens is that? 1, 2, 3, 4, 5, 6, 7. And what if I put a nitrogen out here? With 2 H's on it. Would that match? Do I have 9 hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right?
Yes, so Dr. Russell.
Go ahead.
So degree of unsaturation, like a ring counts as 1, right?
Yes.
Okay.
So this is 1 ring and 1 pi bond. So this is 2 degrees of unsaturation.
Okay.
Right? I could also think about doing something like this, similar to that, and then we're gonna stop here. So I'll make another 5-member ring, but I'll put a double bond to nitrogen, right? And then put a hydrogen here, and then that'll be 2, 4, 6. Come on, Russell. Crunch time.
I have a question.
Go ahead.
Like how do you know where the double bond goes?
You don't. It's a proposed structure. All we know is the molecular formula. So we can develop a structure based on that. And it's trial and error. As long as it's a valid Lewis structure with four bonds to each carbon and nothing hypervalent, then you can propose whatever you want to propose. It doesn't have to be that, right? By the same token, if I had a 5 carbon chain and I put 2 double bonds in it and I added an NH2, that will fit too, right? Because it's 2 degrees of unsaturation. And it's just a matter of adding the hydrogens in to make sure that you have 9 hydrogens. And that will be 9 hydrogens also, right? I might have to shrink that down so it doesn't get cut off. So that's 2, 4, 7, and then the NH2 will make 9. Is that right? So it's really there's really no like specific structure that you have to have. It's all of these are proposals. The only way to find out like what that molecular formula, like what the structure is to do NMR like we did yesterday. Because if you just had the molecular formula and nothing else, you need some way to kind of start thinking about how to put together the structure. So the best way to do that is to take the NMR and see how the protons look in that NMR. You do a proton NMR. All right, so we got to stop. We are 4 minutes over time, and we're going to stop recording and stop sharing.